This is TechSNAP, episode 417, for November 29th, 2019. Hello and welcome to TechSNAP, Jupiter Broadcasting Systems, Network, and Administration podcast. My name is Wes, and I'm joined by Jim.
Hi, everybody.
Welcome to the show, Jim. Before we get started today, I'd like to let you know about a great Black Friday promotion we've got going on over at Linux Academy. If you're listening to this show, you're probably interested in things like Linux, AWS, DevOps, containers, and of course, security. And at Linux Academy, we provide top-quality, hands-on online training for all those topics and a whole lot more. And right now, we're running our annual Black Friday promotion that takes $150 off a full year of unlimited training. Visit learn.linuxacademy.com/Jupiter to get a full year of training for just $299. I'll note, too, that it's a great time to sign up because if you sign up during the promotional period and keep your account current, that's the price you'll keep on paying. In what seems to be a reoccurring segment on this show, Jim, you've got another new wireless protocol for the class today.
Yeah, ONPC, the on-off noise protocol of communication. ONPC is it's kind of an interesting case. It's not something that you use on its own. It's an extra protocol that rides on top of existing Wi-Fi devices.
You mean this works with the same hardware I'm already using all over my house?
Yeah, absolutely. Now, to be clear, it doesn't currently work with absolutely everything just because the code hasn't been written. The researchers were using OpenWRT on Netgear routers, I believe, and a very common Wi-Fi chipset used for IoT-grade devices. But yeah, it can work with anything.
Okay, so why do we need another protocol? What is ONPC targeting?
You know, the honest answer is probably most of us don't really need it, but it does fit a really cool niche use case. The researchers that created it, they were doing studies with members of the general population that involved deploying IoT sensors around people's house and using existing house Wi-Fi to batch the data that the sensors had collected back to the university. And, you know, the problem was that it was relying on people's Wi-Fi at home. And if there's one thing that we all ought to know by now, it's that most people's Wi-Fi absolutely sucks. And so frequently, you know, these devices would drop off the network and they wouldn't upload data for a while. And that left the researchers with a difficult choice to make. They could either wait and see if the sensor showed up again, in which case, you know, it would just cheerfully batch up all the data that it, you know, had not uploaded already. Or, you know, if it didn't do that, then eventually they're going to have to, call the study participant. And if it turned out that the sensor had actually been, you know, unplugged or broken the whole time, then that was data that wasn't actually being collected and they were never going to get. And that was a big deal.
Yikes.
Now, the problem here is that, you know, every time you call these folks because, you know, you can't find your sensor, you're annoying them. You know, you're making them go, you know, look at the flashing thing that, you know, they're not even really supposed to be thinking about.
No one wants that.
Yeah, if you irritate them enough, they're just going to drop out of the study. They're going to unplug all that stuff, throw it in a box and say, come get your crap. I don't want you calling me anymore. So that's where ONPC comes in. Basically, you know, when you have these devices that are all over a house, you know, in places where the Wi-Fi, you know, works, but it's kind of dodgy. The idea is that even when the device can't actually connect to the Wi-Fi, basically, it can just turn on and off in a coded pattern. And, it's kind of like sending up smoke signals or, doing Morse code. And although you never get a good enough signal for the device to be able to join the network, the router is still actually able to see the changes in the noise floor and recognize that pattern and say, hey, my device is still alive out there. It's okay. It's on and working.
That is surprisingly clever. Are there any downsides, though? I mean, if you're piggybacking on top of Wi-Fi, is this going to cause interference and make that poor home quality Wi-Fi even worse?
No, Wes, it's really not. So, you know, when the researchers were testing this stuff, they did a great job with the research. They definitely are not so great at writing for consumer audiences. They did testing on exactly that issue, you know, trying to find out, you know, hey, will this affect Wi-Fi quality? And what they discovered was when they had a device that was doing ONPC transmission, when they had a test laptop that was doing iPerf, if it was out, you know, towards the edges of the network, the ONPC transmission had absolutely no impact on throughput. It was just lost in the noise floor. Now, if their test laptop, the one that they're running iPerf on, if it was in really, really good range of the AP, so it could basically be successfully, transmitting frames with no errors pretty much 100% of the time, they could see up to a 20% performance loss from the ONPC transmissions. Now, the thing about that is, you're not usually actually that close to the AP and, have this really great connection to begin with. But B, even more importantly, you have to understand that that device that's doing the ONPC transmission from all the way out on the edges of your network, it was already there. And if it wasn't doing ONPC, it would be connected to the actual network and sending and receiving a lot more traffic than it is with ONPC. So although you did see this 20% performance drop with ONPC running, it seems really reasonable to think that you would have had a much worse performance drop from something all the way out, in the hinterlands of the network that's actually trying to move data back and forth.
All right, well, I can certainly see how this would be handy, even if only for a few niche use cases. Is this going to work with the hardware right now? Are consumers going to need to get new gear to take advantage of this? And are there actually plans to adopt this as a standard that would be in consumer gear?
So the issue here is, it will absolutely work with any Wi-Fi hardware anywhere because it rides on top of the existing Wi-Fi protocol. The issue is that what you need is new software. So if it's not baked into the drivers for your consumer hardware, then you're either going to need, custom or modified drivers, or you're out of luck. That's why on the router side, they were using OpenWRT because that made it much easier for them to, build in the ONPC receiver code. And, like I said, over on the sender side for their actual sensors, they're using some very basic IoT sensors that they could actually hack the drivers on.
Love seeing OpenWRT get a shout out there. It's a great open source tool to build on.
I hear some people say OpenWrt, but I refuse to.
Amen. We've recently talked about a different longer range protocol, and that's, of course, LoRa. How do these compare?
Well, Wes, LoRa and ONPC don't really compete. LoRa is very long range, and although it's a low bit rate, it's a usable bit rate, typically 300 bits per second or higher. ONPC is only a single bit per second, and it basically only works a little bit farther out than the Wi-Fi does. So the use case for ONPC, I really don't see one beyond just extending the capabilities of your current Wi-Fi devices without having to buy new stuff. If you're setting up an infrastructure from scratch for, very long range monitoring networks, then you should absolutely use something that's actually designed for that and longer range like LoRa. But, if you're already just kind of making do with what you've got and all you need is a way to get a heartbeat on things that aren't quite connected just to figure out whether they're alive or not, ONPC is a good fit.
And it sure is a neat hack. If you want to read more, we'll have some links over in the show notes at techsnap.system/417. Well, speaking of Wi-Fi, we've also talked a bit about Wi-Fi 6 of late, and you had some good advice, which was maybe wait a bit before investing in a Wi-Fi 6 router, as you replace other devices and they'll get support first, and at some point it'll make sense to upgrade. I'm curious what you think of Ubiquiti's new Amplifi Alien, which is mesh capable and Wi-Fi 6, right?
Yeah, it is. It's hard to know what to think of Amplifi Alien until I actually get one on the bench, or preferably 2 or 3, and put it through its paces. The specs on the device look good on paper. The aesthetic, if you like Mountain Dew, Monster Energy drink, and Xboxes, you're going to love the Alien. But the thing that I've found in obsessively testing everything consumer Wi-Fi on the market for the last 3 or 4 years is that specs just don't tell the whole story until you've actually tested something and preferably tested it in a real world, realistic, challenging environment. You just don't know how well it's going to do. Also, I love the idea that you can buy one of these things and use it as a router and buy more of them later and turn it into a mesh kit. I think that's something that the consumers really, really want. I think it resonates with a lot of people. The only thing is it doesn't always work very well. Asus has done the same thing with some of their higher end routers. They call it AI mesh, where you can buy one router and use it as a router, and then further on down the line, you can buy another one and then a third and, call it a mesh kit. Unfortunately, in my testing, it just didn't work well at all. A single additional router used as, just call it a Wi-Fi extender. It wasn't great, but it wasn't terrible. but adding a third one didn't actually get you any benefit whatsoever over just having two.
Well, that is disappointing. It also seems like this unit is a little bit pricey, at least for a single unit.
Yes, absolutely. It was $380, I think.
Ouch.
I actually thought, when I first looked at the press release for it, I got kind of excited because I saw, Wi-Fi 6 mesh and $380, and I thought, oh wow, it's the first, really affordable Wi-Fi 6 mesh kit. But no, it's just for one device. You're basically going to buy a crappy used car by the time you get three of those things to make a real mesh kit. You mentioned before that I had advised people to hold off on buying the router. Like, you should absolutely be looking for Wi-Fi 6 capable devices right now, but it's not really the right time to jump in and spend a ton of money on a new router. And I haven't done much testing of Wi-Fi 6 routers yet, even with Wi-Fi 5 devices. But I also want to make the point that right now, Wi-Fi 6 itself is kind of a mess. A Wi-Fi 6 router may or may not be great to connect your Wi-Fi 5 devices to compared to a really good Wi-Fi 5 router. But also, even when everything is Wi-Fi 6, some of the most compelling features in 802.11ax Wi-Fi 6, they're not turned on yet. OFDMA is the big one. That's the one that allows lots of devices to transmit and receive at the same time on, lots of little tiny slices of frequencies without increasing latency. And nobody has that enabled in their routers yet.
Is that just taking some time to work out the kinks?
Most of what I know about that so far has been, discussions with Tim Higgins over at Small Net Builder. He has been very extensively testing Wi-Fi 6 from, more of an engineer's point of view than a consumer point of view. He's said that he told me that OFDMA is not turned on in any of the routers. It can only even be enabled on a few of the chipsets that are out there right now. And apparently actually enabling it doesn't really do you much good. There's apparently still more to be worked out with that.
Well, I guess we'll just have to wait for some more real world tests. Here's hoping a review unit lands on your desk sooner rather than later.
All right, Wes, well, that's enough about how much Wi-Fi sucks. Let's talk about how much SSDs suck.
Oh boy, yeah. I noticed an interesting paper over at the IEEE Symposium on Security and Privacy titled Self-Encrypting Deception, Weaknesses in the Encryption of Solid-State Drives. And some researchers from the Netherlands did some fascinating research analyzing hardware full disk encryption on several different brands of solid-state drives, with some unfortunate conclusions that, given the state of affairs affecting roughly 60% of the market, currently one should not rely solely on hardware encryption offered by SSDs, and users should take additional measures to protect their data. Is this just a well-duh conclusion, or are there some interesting results here, Jim?
I think it's a little bit of both. I feel like if you're really serious about encryption, you should probably never just rely on, whatever came in the tin with the consumer item that you bought. But it's certainly a confirmation of that. Seeing that the encryption is too weak to be relied on in these solid state drives, it just really underscores the conclusion that, some of us already had, which is, don't throw away your BitLocker or your Lukes or whatever you're using for software encryption just because that's out there. It's also interesting because, we know it's possible to do really good by default hardware decryption. As much as I hate Apple, they're one great example of that. The entire U.S. government is trying to convince Apple to decrypt an iPhone for them, and Apple's like, no, and it just stays encrypted.
Right. Theoretically, there are a lot of nice properties of using hardware encryption, but there's also some problems.
Oh, absolutely. Doing it all in hardware, it means that you can, in theory, have a stronger algorithm with lower impact on latency or throughput because you're doing it all in, purpose-designed FPGAs rather than having to do it in general purpose computing. So that's great in theory, but you have to be really, really sure you can trust that vendor to be using the right hardware and configuring it properly and not screwing up along the way. It's kind of a lot to ask.
As we know, crypto's hard and easy to get wrong.
Crypto is hard and easy to get wrong. And, that moves us on to the related topic, how to securely wipe an SSD. We all know that we can securely wipe a hard drive by writing it with zeros. And then if you're, really paranoid, writing it again with ones, maybe writing it with a couple of random patterns after that, use some tool like DBAN.
A week later, your drive is erased.
But that doesn't necessarily do the trick on a solid state drive, because where conventional hard disks are basically pretty dull, and if you say, hey, I want to write to Sector 8 on track 3, it says, sure, boss, and it does it. You can issue the same command to a solid state disk and be like, okay, I know what you want me to do, but I'm going to do this other thing instead that minimizes the amount of wear that I'm putting on the drive. So you have access to a logical address space on the solid state disk, not the actual physical address space. And just because you write zeros to every page that you can find on a solid state disk, that doesn't mean that you've overwritten the ones that the disk is, kind of reserving and it's sort of, holding out from where you can see it. And somebody else later can connect to that disk and use a lower level tool, and they may be able to get access to a few pages of data that you didn't successfully wipe.
In a lot of the guides I've seen, they almost always mention secure erase. If we're being paranoid and we're taking our disk security seriously, can I trust secure erase, the implementation baked into my drive?
Well, you don't really have a whole lot of choice. You want to see what secure erase is doing. If it's actually overwriting all the cells in the disk, then you can probably trust that. But if it's more like, the technique that is used on modern smartphones, where you literally just delete the encryption key, well, we already covered the fact that you can't necessarily rely on the hardware encryption. So if you didn't rely on it to start with, then you probably can't rely on that now. Just delete the key and nobody will be able to get at the data.
Right. As always, you're trusting that the firmware is going to handle that properly. And that's a risky proposition sometimes.
So the real answer is, if you want to make absolutely certain that nobody gets to the data on your SSD, you pull it out of the computer and you put that little plastic sucker on the table and you whack it with a hammer into little tiny pieces.
Simple, but effective.
And believe me, it's a whole lot easier than drilling holes in old conventional drives.
And a lot of fun.
Wes, it's super basic, and we're going to get a little bit more in depth here. But before we do, I feel like it might be handy to get some extremely simple terminology out of the way to help people understand what we're talking about. And that's talking about inference and training. When you look at machine learning or advanced intelligence, whatever you want to call it, workloads, particularly when you're working with neural networks, there's two big modes of operation, and they're very different from one another. One is training. And in training, you take a neural network and you feed it a whole bunch of data that constitutes a problem space. And you let it do what's basically just a drunkard's walk through the whole space. It's looking for patterns. It's looking for how to solve the problem, how to maneuver through it. And this takes a very long time. It has to go through it repeatedly, and it's adjusting weights and values so that it learns how to work with this space. That's the training phase. Now, once the network is trained, the next type of workload is inference. And that's when you take the neural network that's already been trained and you feed it a new piece of data that you expect the trained neural network to be able to tell you something about. Like, this is a person, this is a dog, this image is a cat, yes, there are 3 traffic lights in this picture, that kind of thing. Inference happens much more rapidly than training does because you're not working through this entire problem space, like looking at every possible move you can make on a chessboard. Instead, you're just looking at this one thing and doing what you already know is the right thing to it.
Right. You've already learned that task. You don't have to spend that time. The model's able to just be applied to whatever data. And that's what makes these tools so powerful. You have somewhat raw forms of input data, and you're able to almost automatically build up representations, learning, understanding, at least to some extent, the right things to do, and then apply it widely. Unfortunately, that takes a lot of computing power.
Well, Wes, that's true for training, not so much for inference. Like we talked about, there's a much, much larger problem space to work through with training, and your big metric there is going to be throughput, because you're trying to just ingest this enormous amount of data and process it as rapidly as possible and get done with it. Now for that, you're usually going to want, we still call them GPUs, but it kind of feels like a misnomer, Tesla V100s or similar. Their origin might have been in, GPUs, but there's no video output on them and you don't plug them into a monitor. They're really just for these types of calculations.
Right. Just a whole bunch of matrix multiplication.
But now once you've got that neural network trained and you're doing an inference workload, you just want to hand it a picture and say, does this have a cat in it? You can do that on much, much less expensive and simpler hardware. And now your metric is usually not going to be throughput. It's not really about how many images per second you're processing. Typically, it's going to be about latency. How quickly can you satisfy this human that's asking you what this thing is?
And with different constraints, it makes sense that you'd want different hardware for different applications. Hardware tailor-made for inference, or hardware tailor-made to be efficient at training.
Exactly. So up in the cloud to train these neural networks, we've got supercomputers with massive banks of $7,000 Tesla V100 GPUs. Doing the inference, on the other hand, you can do that on your phone. And in fact, most modern smartphones have special NPUs, neural processing units, that they can offload tasks like this too, rather than just doing them on the main CPU for the phone.
A great resource about how some of this has been changing, how we've started to find dedicated chips in edge and mobile devices and on servers, is a recent paper by Jeffrey Dean of Google Research, all about the deep learning revolution, as he calls it, and the implications for computer architecture and chip design. And it's got some interesting history of how this all happened. A lot of the algorithms behind AI, the current trends of machine learning and neural networks, well, they were developed decades ago, but it's only been recently we've actually had the computational horsepower to make it practical. And because you can make more assumptions, you can simplify the hardware and pack more dedicated functionality for just the features you need on that hardware, including things like they happen to be very tolerant of reduced precision computations at times, and most of the computations performed by at least most models are just different combinations of a relatively small handful of operations like matrix multiplication and vector operations. And because you can make more assumptions about the workload, you can make customized hardware with just the features you need and more of them per square inch.
Like Intel's AVX 512 extensions, more commonly known as Deep Learning Boost.
Exactly.
Which, by the way, I can confirm that Deep Learning Boost does live up to the hype. When I ran some benchmarks using a framework called AI Expert, I used Intel's OpenVINO tool for image recognition on the SSD MobileNet V1 and ResNet 50 datasets. And I saw a throughput increase of 2 to 3 times from the i9 9980 to this year's i9 10980, which is particularly interesting because in every other respect, the 10980 is actually a little bit slower than the 9980 was. But for inference workloads, double to triple the throughput.
Wow, that is impressive. And I think a sign that we'll be seeing more machine learning applications, not less. In the same vein, you and I were chatting before the show, Jim, and you remarked that not everyone realizes the extent that machine learning algorithms are already being used in everyday life.
Yeah, it's very easy to miss if you're not paying attention, but AI is absolutely everywhere. When we talk about these, deep learning and neural networks, it's not a near future thing. It's an everywhere you look kind of thing. When Facebook says, I think that there's a woman, a cat, and a horse in this picture, that's AI that you're looking at that did that tagging. That's neural networks that were trained on a whole bunch of images and learned to recognize patterns. If you have an Office Insider account and you sign on to Office 365 and open up a spreadsheet, you have access to natural language query boxes where you can highlight a table and say something like, show me the best-selling product from Q4. And it understands that and gives you the relevant chart in a series of related charts in like a second or two. That's AI. That's neural networks. When Google or Siri or, God help you, Bixby or Cortana, answer a question that you ask natural language. Again, that's AI. That's a neural network.
Yeah, with larger and larger data sets and advancements and refinements in the algorithms themselves, there's some impressive and widespread results these days. But it's also important to keep in mind, you need to be aware of AI snake oil.
Yeah, Wes, you showed me a link to a really cool paper from Princeton University professor of computer science, Arvind Narayanan, How to Recognize AI Snake Oil. And we probably don't have time left to go into everything that he covered in the paper, but a lot of it boils down to, yes, AI is doing all these really cool things. It's very good at recognizing images, and it's pretty good at recognizing and transcribing human naturally spoken voice into text, and it can isolate a lot of patterns. What it can't do is, it boils down to magic. It can't do magic.
What do you mean by magic?
One really good example is there are companies out there that are claiming that you can just take a video clip, any video clip of like 30 seconds of somebody that you're thinking about hiring. They don't necessarily need to be talking about the job or anything in particular, just video of them for 30 seconds and feed it through an AI routine, and the AI will tell you whether or not that person is going to be a good hire. Well, that information is not in some random arbitrary 30-second video clip, so it's not there for an AI to get out. Again, it can't do magic. If the information's not there, it can't find it. Another thing that's important to realize is, a lot of people get upset and say that we shouldn't even be using the term artificial intelligence because these things, they're not intelligent in the sense of, like HAL from 2001: A Space Odyssey, which they aren't. The thing to understand is that that's a very different thing. That's actually not artificial intelligence. When you look at HAL from 2001 or Kit from Knight Rider, or you name it, the machine that you can talk to and have a conversation, it's like a person in there in the box. That's artificial general intelligence, also known as strong AI. We're nowhere near having strong AI. Artificial intelligence really just refers to technologies that work in a lot of the same ways that our brains work. And it is possible to compare them to animal intelligences in a very rough sort of way. But if you did, our current AI, it's roughly on the level of a worm. Those worms can be trained on really complex, high-level sets of data that an actual real-world worm would never have access to. But your AI worm, it can be trained on that. It lives that. It thinks it. It breathes it. It eats it. That's what it does. And so it can find correlations in that data and manipulate them in ways that aren't at all obvious to us. But it still isn't magic.
That's absolutely right. The paper's got more great examples and some guidance on areas that have actually seen some rapid progress recently. So go check that out. We'll have links to all the papers and everything we've talked about today over at TechSNAP.systems. And I'd also like to remind you to head on over to learn.linuxacademy.com/Jupiter to take advantage of our Black Friday sale and save $150 off a full year of unlimited hands-on online training. That's learn.linuxacademy.com/Jupiter. If you'd like more Jupiter Broadcasting shows, head on over to jupiterbroadcasting.com for the full catalog, live times, and ways to get in touch. If you'd like more Jim, you can find him writing over at Ars Technica, and he's on Twitter at
JRSSNet.
I'm there too, at Wes Payne, and the whole network is at Jupiter Signal. Thanks for joining us.
We'll see you in a couple weeks, everybody.